Hi guys, it's Friday. So if you tell me that I can talk about anything for a couple of minutes, um, then I I think it's pretty obvious what I'd choose. So without much further ado, I'm going to show you how to do two math problems. Both of these come from the Putnam competition, which is given to undergraduate students each year, and there are 12 questions on it, split up into two sections of 6 questions, one in the morning, one in the afternoon. Each session is 3 hours long, so basically you have an average of 30 minutes for each problem. And out of these 12 questions, each one is worth 10 points, so there's a maximum possible score of 120. And the median score is often a single-digit number, and last year it was even 0. So basically, more than half of the undergraduates who took a math competition because they wanted to take it to see how well they can do, people who like math, more than half of them got no questions right. So, well, I said without much further ado, and then I talked for a minute, but here are the two questions. So this first one, I think it was on the 2002 Putnam, and this is the reason that the median score was almost a 10 that year. So the problem is you take a sphere and you put 5 points on it. So now show that that there exists a closed hemisphere that 4 of the points are contained in. So basically, then take basically the equator. There are points that are either on that or north of it, basically. If you're saying the northern hemisphere is your closed hemisphere, the question is saying there's at least one closed hemisphere like that contains at least 4 of the 5 points. So at first this seems kind of ridiculous. So basically let's start, instead of drawing a sphere, I'll draw just a sort of circle because it's easier to draw. So you have your circle. So then your first 2 points, no matter where they are, they define a line. And so then these 2 points define a line shown there. That line marks 2 hemispheres. So then the next point has to be in one or the other or both. So let's say it's in one of them. So now you have 3 points in this one and 2 points in that one. So now the only way that you won't get a 4th point in here is if you put one over here. So now with 4 points you have 3 points in each hemisphere. So then the last point has to go in either one hemisphere, the other, or both if it's on the center line. So you have 4 points in at least one of the closed hemispheres. The second problem is a bit more difficult. I think this one's from 2005 or so. But again, it's not too hard, and I could solve this one by myself. So the question says, basically, take any rational number, p over q, and you can express that as, and you can take p over q and you can express it by multiplying and dividing factorials of primes. So a factorial, like 10 factorials, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So you just basically multiply all of the integers, all of the positive integers that are that number or less. So basically, the first thing you do, so start by saying, okay, well, if you can do p over q, then you can just do all of the integers if q is 1. So basically, so to do this, you prove it by induction. So you say basically you assume that it's true. You prove it for a trivial case, usually 1. So say basically you can express 1 by multiplying or dividing factorials of primes. 2 factorial over 2 factorial gives you 1. Okay, it's true for 1. Now you say if it's true for n, then it's true for n plus 1. So then basically if it's true for 1, it's true for 2. If it's true for 2, it's true for 3, all the way up to infinity. So then basically you say, okay, so if it's true for all of the numbers up to n, this is actually strong induction since you're assuming it's true for everything up to n. Weak induction, weak induction is basically only using n, but for this you need strong induction. So you say it's true for all of the numbers up to n. So then for n plus 1, there are 2 cases. The first one is n plus 1 is a prime number, so then you do n plus 1 factorial over n factorial, and you can do n factorial, so then there you have you can do n plus 1. If n plus 1 isn't prime, then that means that it has a unique prime factorization, so you can express it by multiplying primes together. So then you just take those primes, you get them, which you know you can do since they have to be less than that. And so then there, you have all of the integers. Then you just say, okay, that's p. You can also do it for q. So you can get it for both p and q. You can do whatever you want, all the positive integers. Therefore, all positive rational numbers must be able to be expressed in this way. Now, if you want a challenge, which I wouldn't really recommend, you could do find the minimum value of the absolute value of this whole quantity, sine of x plus cosine of x plus secant of x plus cosecant of x plus tangent of x plus cotangent of x. Find the minimum value of that. No one in the math problem solving club here could do it. I thought I did, but then I realized that I had an error somewhere that probably made it much easier than it should have been. And so, Alyssa, I'll see you Monday. Emma, I'll see you Wednesday. Bye.